Hello, this is Dr. Christy Patton-Lukes, your instructor for Chemi 3111. And for Lab 1, we are going to be looking at Taylor series. But first, what I wanted to do is go back and address the results from Lab 0. And this is different data than what you guys took, but in a previous semester I had the students measure the specific gravity of a wood block. And different groups did their techniques very differently, came up with different estimates. And so this is a summary of all of their data, okay, with their error bars, okay? So if you looked at this and you had all of these repetitions of the measurement, what would you say is the specific gravity of the wood block? Now you may do lots of different things, but one thing that I do is when I first scan these numbers, I see that one is seriously off. I believe they just made a decimal error and it's probably 0.0 or 0.543, but I don't know that, so really I should scratch this one off and I would call it an outlier. But so then I might take the average of the remaining values. What about choosing what my error limit is? There are many techniques that you might use to do this. But in a case such as this, frequently what I do is I list what is the minimum and the maximum. And so, in other words, 0.541 plus 0.005 and 0.541 minus 0.005. And make a list of all of the minimums and a list of all of the maximums. And then I could use that to determine what error bar would encompass all of my various numbers. So the largest maximum, the smallest minimum, perhaps would be something that I might want to choose. You would need to look at the data and decide. The reason that I wouldn't just average these, well, first of all, these student groups had taken this measurement in very different ways. And so therefore I think that there is meaning to the fact that they have, different order of magnitude on the error bar. And so that needs to be recognized when we do our final error bar. But the other thing is, notice that a couple of these groups had given many significant figures in the error limit. And I want you to be aware that you need to always do just in your error limit, it's going to be one significant figure, and it needs to match the final digit that you show in the actual value, the specific gravity. So that, I also wanted to discuss significant figures a little bit before we get too far into the course. The rules for determining significant figures still apply, but a lot of times that's their logic is going to supersede all those rules, and sometimes it's just faster to just kind of use good sense. The most important thing I need you guys to know is that if you measure more significant figures, it costs more money. So I had you do this mass using a kitchen scale. I could have gotten an extra significant figure by doing a laboratory quality scale, or a very good laboratory scale could have gotten me 2 more significant figures. Okay. Most of the time the budget for this class is going to get us 2 or 3 significant figures. In industry, usually you can afford to get to 3 or 4. But if you're ever going to more than 4 significant figures, you're talking about some expensive laboratory quality equipment that is just not realistic. And so a lot of times I just use the number of significant figures that are reasonable for the sort of calculation that I'm doing. Now, the other thing is we're going to be doing things that have lots of intermediate steps in the calculations. And on those, I treat every intermediate step as if it had infinitely many significant figures. I try to not round my intermediate steps. And then the final answer, at that point, I round to an appropriate number of significant figures. Now, in this lesson, what we were talking about was series solutions. and the capital sigma summation sign. And a lot of this was about order of operations. And so, for instance, here I have just some various functions here, and let's just think about these a little bit. So if I had x over 3 plus exponential of negative x squared, this means I'm going to take the number here and then divide that by 3. I'm going to take that answer, I'm going to save it, and I'm going to add it to the answer for this. And here I'm going to take x and square it and then take the negative of that. So every time I will get something negative, because x squared will always be positive no matter x. And so e to the negative x squared will be added to x over 3. In this expression, a is going to be a series solution. So k factorial over x to the minus k, or times x to the minus k, means I'm going to go through this for a fixed value of x, and I'm going to increase k as my counter, 0, 1, 2, 3, appropriate to whatever I had said on the summation sign underneath. Usually it starts my counter. This is shorthand notation, so I didn't include it here. But so I would do 0 factorial times x to the minus 0 plus 1 factorial times x to the minus 1 plus 2 factorial times x to the minus 2, etc. And similarly for b, this is a similar sort of expression, but I'm going to take 2x plus 1 and then raise that to the minus k power. Now where this gets tricky is when you get to something like c equals a over b, and a is this series and b is this series. Because they are series, remember I'm adding up infinitely many terms and k is changing each time. A lot of times people look at this and say, oh, k factorial top and bottom, I'll just get rid of that. No, don't do that. If you actually wrote it out term by term, you look at it and you are not tempted anymore to do that. But with the summation sign, you are tempted to. So I really recommend on series solutions, be incredibly careful if you're ever doing any simplification. Okay? Generally, don't do the simplification. You're probably going to be wrong unless you've written out some terms and can see that, oh, yes, indeed, this really could be simplified. Okay? The other thing that we talk about in these lessons is the difference between relative and absolute error. So on those specific gravity measurements that we took in Lab 0, I asked you to give me a number. So that would be an absolute error. If I asked you to tell me percentage, okay, and so those measurements that we were looking at for the wood block, 0.543, plus or minus 0.005 means that I'm looking at something that is 0.005 over 0.543, so I'm talking about a 0.1% error. But if it was 0.05 was my error, that would be a 1% error. And so I'm talking about it as a percent of the whole. We use these when we do series solutions. So our error is usually our last term plus all the stuff smaller than that. And we can either do it on a relative basis or an absolute basis. Frequently, we're going to choose to do the relative basis because that allows us to scale things. But an absolute basis also can be used. So you need to be very sure that you are reading the problem statement carefully, or listening to the instructions of your boss or the request of your boss very carefully to know which of these they intend. So today's lab, we're going to be doing an example from a heat transfer textbook, and you don't need to understand too much about this, but we have here a case where we've got an object. Okay, so here's an object here, and we want to know what's happening to temperature if I maintain one side at temperature theta naught and the others are all at temperature 0. Okay. And so if I do this, what's going to be the temperature distribution throughout the rest of the object. So we have boundary conditions where x is 0 for any y. We have theta naught where x is b. So 0 is theta naught, b is 0. Where for any x, where y is positive a at 0 or negative a at 0. So we're implying that this is the x-axis across here. Now in this problem, the solution, after a lot of work that is not for this course, we end up with this as our answer, that theta over theta naught is 2 times the sum from 0 to infinity of negative 1 to the n power, the hyperbolic sine of lambda sub n b minus x over the hyperbolic sine of lambda sub n b times cosine of lambda sub n y. And the lambda sub n is given by this, so you'll see that it's a function of n and that parameter a. So 2a is this distance across here. All right, so this is our problem description, and we have then, this is a formula. And then they give an example where they have an object that is 10 centimeters by 5 centimeters. That's maintained at 100 on one side and the other sides are at 20 degrees. So the thetas are subtracting those, so subtracting 20 from everything. So theta naught is 100 minus 20, so theta naught is 80. And theta on the other sides is 0, so 20 minus 20 is 0. So you see the theta naughts down here in this picture. And then they show you how the A is measured, the 10 centimeters by 5 centimeters. They've moved it to the units of meters. And they want to know what the steady state temperature is at the point x and y equals 1.25 centimeters. So right here at this location. So we're just going to use that formula. We have a value for A, okay, and we have our value for B. So A is 0.05, or no, 2A is 0.05, B is 0.1, theta naught is 80, theta is 0, and we're doing this for x and y equal to 0.0125. Right, we need to be sure that we're working in the same units, meters. And so you should be able to program this using the code that we developed in the lessons this past week. Now I'm going to give you some kind of programming notes here. Now first thing is that hyperbolic sine is an Excel function, but it isn't a Visual Basic function. And so you need to call it from the worksheet. The way I do that is using application.worksheet function dot, in this case, cinch of whatever, okay? But you also can actually go directly to the worksheet and have it read from there. So people do it different ways. But this is a nice way of doing this because I can do application.worksheet function dot in any of the Excel functions and use that in VBA. Now you are going to need to enter values of x, y, a, and b into your program. And I don't care whether you're reading it from the sheet or just typing them into the program. If you want to set up a little input box, you can do it any way you want to, but you do need to make sure those values get entered. I'm going to make a suggestion that when you edit existing code, do not delete a line ever. Instead, just add a little single apostrophe to the beginning of the line. That way it's not going to go away. You haven't lost the code, but the code will ignore it. So what you're doing is you're commenting that line out. And so that's really helpful when you're doing something like this where you're taking existing code and editing it, because sometimes you end up destroying things that you really didn't want to. Now in this case, you're not going to need the factorial part of your routine. Factorial is not in this function, so you could comment that out. But you still need to have the error limit portion of the routine. If you ever comment that out, you have an infinite loop. Now, when you end up with an infinite loop, because it will happen to you sometime, I'm sure, okay, escape is best friend keyboard. This is using Windows. If you're in a Mac, then you know the magic things to do for that one. If you really get desperate, the Control-Alt-Delete will also break the code. But you will need to make sure whenever possible before you run your code that you left in checking the error limits. Otherwise, it will be an infinite loop. Other thing is that the formula on the handout uses N as the counter, and we were using K. You can either change the formula or you can change your code, but just be careful. That's something that a lot of people get wrong. These are my suggested code snippets. So after the for statement, if you'll put in something that defines lambda and arctangent, for arctangent of 1 is pi. So this portion here represents pi. Anyway, so that's lambda, and then I'm calling that worksheet function for cinch1 and cinch2. So cinch1 is the one that's in the numerator that has b minus x. Cinch2 is the one in the denominator. And then therefore this is my term. And then you can get rid of the old term statement or just comment it out. Okay? Be sure you keep the test for the error limit, and be sure you keep the line that says sum equals sum plus term. And it should work fairly directly. Now, how will you know if you got it right? Well, I chose an example from a textbook, and they had a solution. So here's their solution. They came up with value of t, okay, which is 54.8 degrees C, or as theta, if you're doing theta over theta naught, of 0.4350. All right, so this allows you to check your work. Try this. Be sure to contact me if you have any issues, and then move on and do homework 1 and start the lessons for lesson 2. Thank you very much for your time.